Hello, I'm Richard Grissenthwaite, Arm's Chief Architect, and I've had the privilege of leading the Arm architecture for most of the last 20 years. Simon has just talked about how Arm's partnering ethos has led to a hugely successful global ecosystem of technology companies. The technical foundation of that ecosystem is the Arm architecture, which in essence defines the behavioral contract between the hardware that Arm is responsible for and the software that runs on it. All of the 180 billion plus Arm-based devices that have shipped over the last 30 years use the Arm architecture and so can run software from the Arm ecosystem. But the architecture is not a static thing. We keep on innovating and evolving it to meet the ever-changing needs of the computing world. In the 10 years since we introduced 64-bit processing in Armv8, we've added a number of extensions, such as improved support for virtualization, addition of float 16 and bfloat to substantially enhance the performance of machine learning, and a number of security enhancements, including increased resilience against return-oriented programming and support for a secure hypervisor. Innovating the Arm architecture never stops, and so today I'm going to talk about Armv9, the next major enhancement to the Arm architecture for the decade ahead that will apply across all of our CPUs, from the smallest microcontrollers to the largest service-focused designs. In our increasingly connected world, we're seeing Arm processors being used at all stages in the life cycle of data. The collection of data often starts with ultra-low power IoT devices based on the Arm M profile processors, or from the Arm-based smartphones that virtually all of us carry all of the time. These connect through the various wired and wireless networking technologies where Arm has been used for many years and continues to be the processor of choice. Those networks commonly take that data to servers, which are increasingly part of the cloud computing environment. And there we see processors such as AWS's Graviton2 providing Arm-based computing for that data. Furthermore, where scientists really want to throw immense computing power at the data, they can use supercomputers based on Arm, including the world's fastest supercomputer, Fugaku, which is powered by Fujitsu's Arm-based SoCs. Looked at from this perspective, we can see that in years to come, virtually all of the shared data will be processed by Arm processors at some stage through its lifecycle. As we go to the future, the demands of managing the immense amount of data being collected means that we will see increasing processing throughout the network. Today, many of the networks just act as a relatively simple pipe carrying the data. But as the volumes of data grow, data must be processed with ever-shrinking latency, so requiring increased computing power and standardization of systems at the edge of the network. We see that this will require new components for performing these computing tasks. The beauty of Arm's approach of providing computing IP components, such as CPUs, GPUs, and NPUs, is that it allows our semiconductor and computer systems partners to develop the purpose-built systems that they need for the emerging challenges. This harnesses the power of Arm's deep understanding of computing components, which will be covered by my colleague Peter Greenhalgh, with the fundamental knowledge of the target markets and system-specific challenges that is the core competence of our partners. Our partners have been doing this for many years in the mobile space, of course, but we are now seeing this approach being used much more broadly, and we believe that purpose-built system design will be the key to innovation in all forms of computing. Different computing problems need different mixes of computing components. Many IoT devices need to interpret their worlds, and a combination of the M-profile cores with the Ethos U55 micro NPU is perfect there. In automotive systems, partners will increasingly be combining many large and small CPUs with GPUs, NPUs, and their own IP to generate the right computing solution for those autonomous systems. We see the same thing going on for servers, networking, in our client devices, and across the computing spectrum. Now here there is a balancing act about having the right amount of standardization. Too much standardization, and the partners cannot develop the purpose-built solutions that work for them. Too little standardization, and we run the risk of having low-value, same but different solutions that injects cost into the software ecosystem for no real benefit. We've seen the value of this balance in the server space already, where, as part of avoiding needless variation while allowing valuable differentiation, we introduced the server-based system architecture, SBSA, and its associated validation program, Server Ready, to drive the right amount of standardization. This has proved to be very successful with our major server silicon partners and OEMs such as Lenovo, HPE, and Advantech having their products certified already. As we look to the networks of the future and the growing use of computing at the edge of those networks, so we are broadening the scope of system standardization. Arm has announced System Ready, which extends the concept of the Server Ready program to a broader set of devices from the cloud to the IoT edge to enable interoperability with the generic off-the-shelf operating systems and hypervisors. This standardization of the necessary parts of these systems is key to ensuring that the software investments that Arm and its ecosystem partners are making can be used as widely as possible. My colleague, Mark Hambleton, will be talking more about that later. Given that Arm's computing technology is being used in some way to touch virtually all of the data in the network, Arm and its ecosystem clearly has an immense responsibility to provide the best experience for handling the world's data. For this reason, we've been working with lead partners on a set of major extensions to the architecture called Armv9. Armv9 is a rolling program of substantial enhancements to the architecture that we'll be deploying over the next few years, increasing the computing capability in the widely applicable areas of digital signal processing and machine learning, and improving the security and robustness of our systems. These Armv9 technologies will be used in all three profiles of the Arm architecture: the A profile for general-purpose compute, the real-time processors of the R profile, and the microcontroller-focused M profile. Over the past few years, we've seen machine learning and artificial intelligence as being one of the big emerging trends in computing. Machine learning has become a ubiquitous part of the computing paradigms that are used in all sorts of systems, and we expect this to grow over the coming years. Machine learning will apply in the endpoint devices, at the edge of the network, in all sorts of different applications on our phones and laptops, in the computing brains of our cars and factories, and in the servers in the cloud. More than 90% of top businesses surveyed report having an ongoing investment in artificial intelligence. And by 2025, more than 90% of new enterprise applications will have machine learning embedded within them. The ubiquity and range of these machine learning workloads means they are not going to be addressed by a single class of solution. Therefore, all of our computing devices will benefit from increased hardware support for machine learning in CPUs, GPUs, or in specialized NPU processor elements. There is also an opportunity to work with NVIDIA to use their machine learning innovations and expertise to enable specialized computing solutions for our partners. My colleague, Jem Davis, will give an overview of the range of technical solutions that Arm is working on for machine learning, spanning a whole wide range of problems. Defined by the Armv9 architecture, CPUs are gaining new vector processing capabilities in order to improve both machine learning and digital signal processing. This is building on the vector extensions that we developed in conjunction with Fujitsu and others, and which are used within the Fugaku supercomputer. That technology was designed in a scalable manner so that the concepts used for supercomputers can be applied across a far wider range of products. We've added increased functionality to create SVE2, the enhanced scalable vector extensions, to work well for 5G systems and in many other use cases, such as virtual and augmented reality, and also for machine learning within the CPU. Over the next few years, we'll be extending this further with substantial enhancements in performing matrix-based calculations within the CPU. In my view, security is the greatest challenge that computing needs to address in order to reach its full potential. Our lives are becoming increasingly interconnected, and so more and more of our private data is being held on computing systems that most people have very little understanding of. This makes them a very attractive target for security attacks. We know that cybercrime losses annually are projected to be approaching some $6 trillion worldwide by this year, and this is set to increase further. For the IoT space, one of the biggest challenges is the security of the myriad of endpoint devices collecting data and interacting with the physical world. We've all seen examples of bad security in these devices, and a lot of this comes from designers not applying tried and tested security practices and not understanding the threats that these devices will be exposed to. To help with this, Arm has worked with partners to develop the platform security architecture as a set of standard threat models, approaches, and practices for endpoint designers to use. This is combined with a tiered certification scheme that will allow purchasers of this equipment to be more confident of their security properties. These same principles extend to the edge computing devices that will be part of the more distributed cloud of the future. The security of these devices will be paramount, and so part of the system-ready program involves ensuring that the security architecture of these systems is compliant with best practices. Looking to the future, computing will become a distributed utility where sessions can be run on the most appropriate platform at that time. In this environment, the ability to trust the computing infrastructure will be a crucial element in ensuring that people will feel confident about the security and privacy of their information. This infrastructure will also be a very attractive target for cyber criminals intent on stealing our data. For this reason, we see a growing interest in confidential compute, by which we mean the protection of data in use. This involves performing computation in a hardware-based secure environment to shield portions of code and data from access or modification, even from privileged software. Today, the traditional model of computing places an immense amount of trust on the operating systems and hypervisors that applications are run on. Confidential computing removes the assumption that the privileged software that is responsible for running the computing system needs to be able to see or manipulate the data of those running sessions. That removal will make it far easier to trust the computing infrastructure. Later this year, we'll be disclosing in more detail the Arm confidential compute architecture, which builds substantially on the strong foundations of TrustZone. The Arm confidential compute architecture will introduce the concept of dynamically created realms, usable by ordinary programs in a separate computation world from either the non-secure or secure worlds that we have today in TrustZone. Realms use a small amount of trusted and testable management software that is inherently separated from the operating system and hypervisor. Using this, for example, a driver's ride-sharing application downloaded from a standard app store and installed on a personal device could dynamically create a realm to hold and work with its secrets in a world away from the operating system and hypervisor. This ensures the protection of the employer's data, even if the phone's operating system is compromised. By preventing the theft of commercially valuable algorithms and data, and ensuring that mission-critical supervisory controls needed by the employer cannot be subverted, it's no longer necessary for drivers or couriers to be provided with dedicated corporate devices. Similarly, over the past year, the pandemic has increased the use of technology to record and manage personal health data, and it is hard to imagine information that needs to be better safeguarded. While the security of current systems is very good, in future, using realms, it will be possible for such personal health information to be safeguarded from end to end. This will give much more security to this data, even if the operating systems of the computers holding this information has been subverted. Analyzing the large number of security issues that get reported in the world's software, a depressing reality is that the root cause of many of those problems really comes back to the same old memory safety issues that have been plaguing computing for the last 50 years. Two particularly common memory safety problems, buffer overflow and use after free, seem to be incredibly persistent over the years, and a huge part of the problem is that they are frequently present in software for years before they are discovered and exploited. I'm sure we all remember Heartbleed, which had been lying dormant in OpenSSL for a good couple of years before it was discovered. Uncovering these memory safety vulnerabilities before they can be exploited is a vital step to improving the security of the world's software. For this reason, Arm has been collaborating with Google to develop a technology called the memory tagging extensions that can be used to find both spatial and temporal memory safety issues in software. These extensions allow software to associate a pointer to memory with a tag and to check that this tag is correct upon use of the pointer. If the access is out of range or if the use of the memory has moved on, then the tag check will fail. so detecting the sort of memory safety issue that is the root cause of so many problems. David Kleidermacher leads the security team from Google that was heavily involved in the creation of this technology and is appearing on one of the panels later today. The memory tagging extensions will be an integral part of the first generation Armv9 CPUs available in the next year, and software support for using memory tagging is being introduced as part of Android 11 and into OpenSUSE. While finding and fixing security vulnerabilities in existing codes is a great step for security, it would be better if, at a more fundamental level, the hardware made it easier to encapsulate accessibility information with the data. This will provide a fundamentally more secure building block for software. Arm has been collaborating with Cambridge University for a number of years on their Cherry architecture, which defines hardware capabilities that give precisely this sort of encapsulation. This could allow for an inherently more secure computing platform in the future, but involves some substantial changes to the way that some systems will be programmed. I've frequently been asked for ways to evaluate this technology with real industrial use cases, as it does seem to be extremely powerful. Fortunately, we've been given an opportunity by the UK government's Industrial Strategy Challenge Fund to create an industrial-scale prototype of this technology. This is a major UK RI programme called Digital Security by Design, where Arm is working with the universities of Cambridge and Edinburgh, Microsoft, Google, and others to explore a major architecture enhancement using capabilities as a new paradigm in computing security and robustness. The demonstrator system of this project, called Morello, is being finished off at the moment within Arm, and the system should be available for all of the Morello partners by the end of this year. This sort of fundamental shift in computer architecture takes a lot of time, but we have huge interest from within Arm's partnership. If the program is successful, then it will feed into a major component of Armv9 towards the middle of this decade. And so, in summary, these are exciting times here at Arm and for the huge partnership that we work with. From our original foundations within the mobile space, we are now providing the fundamental computing components that are at the heart of the ongoing computing revolution. We are partnering with some of the very biggest companies in the world to allow them to build the systems that they need for their computing requirements of the years to come. Looking from the current 180 billion plus Arm-based devices to the ecosystem's next 300 billion chips of the future, we predict a world in which virtually every piece of shared data will, at some point in its lifetime, be processed by an Arm-powered device. We are driving the right amount of standardization that allows for efficient use of all of the software investments, while enabling our partners to fulfill the demands for increasing levels of innovation, customization, and specialized processing. We are enabling our partners with the key computing elements of CPUs, GPUs, and NPUs, allowing them to build the right systems for the years ahead. And our Armv9 architecture technology will provide the building blocks for the real challenges of the decade ahead, adding more DSP and AI functionality within the CPUs, and creating trust throughout the network, defending against the ever-increasing security challenges. Thank you.
Hi, I'm Mark Hambleton and I lead the open source software team in Arm. As my colleagues have already mentioned, a new major Arm architecture revision is a once-in-a-decade thing. Since the early days of V8, we've been developing standards like the Server-Based System Architecture, or SBSA, and the Server-Based Boot Requirements, or SBBR, which were later underpinned by the Server Ready program. They essentially defined the key attributes of server systems and their firmware, which have enabled standard operating systems to boot from common images, which include both Windows or Linux. Following on from the success of Server Ready, we started to look at how we could reach the end goal of any operating system can run on any ARM-based hardware, at least in the A-class. Sometimes we find that standards struggle to catch up to the breadth and diversity of the ARM ecosystem, which is why System Ready has been designed from the ground up to support all the needs of the ARM ecosystem, from the smallest to the largest device. That's where System Ready is coming from. You should be able to take any standard OS and run it on any hardware as long as it conforms to the firmware standards required by the OS. When you think about it, for your connected device to work for 15 to 20 years, it will need to be able to get security updates for those 15 to 20 years. And that could be 10 years after the device manufacturer stopped supporting it. But it's still connected to your network. By enabling standard operating systems to run on these devices, the OS vendors take care of the updates long past the time a vendor support window would usually run. But perhaps most critical of all the work ARM has done with respect to standards is at the firmware layer. Increasingly, the lowest levels of the most secure software, what we refer to as the trusted or secure firmware, are becoming the focus of attacks. If an attacker can gain access to or subvert the secure firmware, they can potentially gain privileged access to the entire system. In V8, we decided to take the lead on providing a standard secure firmware which we would develop in the open for the entire ecosystem to use as the secure foundation for their ARM-based SoCs. This became trustedfirmware.org. And the original offering for the A-class has since been joined by the M-class with an R-class version currently in development. In essence, the community we've created around trusted firmware in the open has delivered a wealth of security software for the ecosystem and enabled a de facto way to boot ARM-based systems. And also a standard way to land secure services for device makers and OEMs. The work we were doing on V8M became the Platform Security Architecture, or PSA, which we're now extending to the A-class. By extending to PSA to the A-class, we're able to provide a set of common security service APIs which will reach from endpoint to cloud based on ARM technology. Once again, the PSA APIs and services are being made available in trustedfirmware.org and in partnership with other offerings such as Opti, an open source trusted execution environment, Hafnium, a secure partition manager, and Embed TLS, a very widely used library for encryption standards. The PSA certified program underpins this. By assessing the certification level a device has achieved, you'll be able to clearly establish if it meets the needs of your specific application. As we transition into the V9 era, we're bringing forth new innovations that build on the trusted foundation of V8. As Richard mentioned earlier, we're introducing the ARM confidential compute architecture, which represents the culmination of 5 years' work to establish the necessary pieces of hardware and software to enable us to deploy separated realms. Confidential compute will be an essential part of enhancing the trust in the systems which host our data, because in today's world of hypervisors, virtual machines, and app stores, there's a larger attack surface on these ubiquitous multi-tenant systems. By applying the general principles behind confidential compute, over time we'll enhance the V9 architecture with realms. Realms enable you to run an application in such a way that your data is protected from inspection or intrusion by the host or any other software running on that host. From the block diagram view of ARM CCA, it looks simple. We're adding a fourth address space. The hardware even looks similar across segments at an architectural level. But from a software perspective, each segment provides its own unique challenges, with each software stack requiring modifications to make use of these new security enhancements. Some of those modifications can be pretty invasive too. So here's what's hopefully a fairly basic explanation of how realms will work. Typically, when you lease capacity from a hyperscale provider, you get a VM hosted on a multi-tenant system, where you get some share of the common address space. In the ARM CCA world, one of the simplest changes will be that instead of the VM being hosted from this common address space, it will be hosted in a realm where the address space is protected from other VMs sharing the system. The same is true on a laptop or PC when you have a second operating system sharing the host resources. I typically run both Windows and Linux on my laptop concurrently, as they help me perform different parts of my job. Those OSs could simply move into realms, and I'm kind of not a typical user. But when you look deeper into how you can use realms, it gets more complex quickly. But through these examples, you'll see how realms will impact our daily lives and fortify the protection of our private data on billions of increasingly connected and diverse devices, powered by the specialized processors Richard referred to earlier. On a typical Android system today, there'll be a mix of non-secure software that runs the core stack, some secure services running under Trust Zone, and maybe some DRM services running as virtual machines alongside Android. One possible future is that some of the secure services could migrate from within Trust Zone into their own realm, enabling a more dynamic environment for that service. But also, the DRM service could move into its own realm, giving it a boost in confidentiality as its data is now protected from the core Android stack. As you start to apply this thinking, you could see more pieces of this complex stack componentized into realms to provide greater isolation from intrusion. For example, take that healthcare app that Richard mentioned earlier. Creating an environment where that app can execute within its own realm, protected from the rest of the system, would provide significant privacy guarantees that it can't make today. But then when you apply this thinking to mixed criticality systems in the robotics or automotive spaces, the benefits become even more obvious. You start to see further benefits separating out services that are feeding safety critical systems and protecting their memory from interference. Look for more information in the coming months. We'll be engaging the software developer ecosystem to help them embrace this new technology and discover how best to deploy and maximize the benefits of this new architecture for the entire Arm ecosystem. Given how critical this future technology will be to protecting the world's data, we're investing now to ensure developers have the tools and software they need for early development, to enable the communities we work with to take this to production. And speaking of protecting the world's data, we expect that virtually every bit of shared digital data will be processed securely on Arm-based systems. Therefore, it's the shared responsibility of Arm and its partners to ensure that all software just works on all Arm hardware. And to enable the breadth of the Arm ecosystem, you have to invest at scale. The decade of V8 probably accounted for more than 10 million software developer hours from Arm alone. The decade of V9 could easily account for more than 30 million software developer hours from Arm as we scale to wherever computing happens. And then when you add in the investment from the Arm ecosystem, you can easily get to more than 100,000 engineers, which equates to more than 1.5 billion software developer hours. And that's probably a conservative estimate. Synergy between the silicon and software developer universes has never been more critical, and increasing this synergy requires standards. By adopting the standards such as System Ready and PSA, the Arm ecosystem can build on the foundation of billions of Arm-based systems. And with the V9 architecture, we will enhance and embed trust from endpoint to cloud. The vast majority of data generated today touches Arm hardware at some point during its life. The majority of developers' code will run on Arm hardware too. Arm is the future of compute in all forms, and the V9 architecture is setting us up for a future where we can trust the platforms we rely on for every aspect of our digital lives. Thank you.
Hello, I'm Jem Davis, Arm Fellow and General Manager of Arm's Machine Learning Group. In today's COVID world, we hear we live in unprecedented times, way too much. But artificial intelligence truly does present unprecedented opportunities, and not just in the usual places. The pervasive growth in Arm-based intelligent endpoints has been staggering, as demand for intelligence grows across the wide range of markets Arm's partners serve, from tiny sensors up to the world's largest supercomputers. And I'd like to give you just a flavour of the innovation taking place somewhat off the beaten path. At Embedded World, Arm recently presented a partnership example. Arm supports practical solutions reducing energy consumption of even the most energy-efficient white goods. For context, your fridge is the second biggest home energy consumer, using 13% of total energy consumed in a household. Today, neural networks running on ARM processors built into appliances enable fridges to learn autonomously and adjust power consumption optimally for the operating conditions. We see over 10% energy savings using machine learning. Tomorrow, AI will transform healthcare. Just take hearing aids. Simply amplifying sounds isn't the solution. ML algorithms balance sounds, making sure output is clean and ideally tuned to the person's unique type of hearing loss, allowing the brain to work in the most natural way possible. We are just scratching the surface of what's possible. ML is everywhere in endpoint devices, opening up the future. But machine learning is not just one compute workload. In fact, let's look at the different types of compute workloads in typical ML inference use cases in these charts. We break down the amounts of processing into whether that type of processing is best mapped to a traditional CPU or a more advanced CPU with vector processing, or GPU if you have one, or finally, if there's a large amount of matrix arithmetic best executed on a specialist neural network processor, or NPU. For these three use cases, you'd ideally build three different systems on chip with three very different types and sizes of processors. Get the balance wrong and you have a chip that's too slow, costs too much because you invested in processing you don't need, or one that uses the wrong processor for the workload and kills your battery or green energy rating. Arm's investment enabling machine learning across all our processors and IP has produced a unique AI platform that delivers multiple IP choices for partners to execute specialized, optimized workloads like ML. Because when choosing hardware for AI, we absolutely see that one size does not fit all. Choices that are right for one partner, one device, or one use case will simply not apply elsewhere. Partners need the right combination of computing elements for their ML usage, but they also need the right balance of all of those compute elements and know that they work efficiently together, meeting performance needs within stringent power and cost limits, and of course, have that compute executed securely. SoC designers are only too familiar with this problem, but now it's more and more critical. General purpose processors used to suit most needs, for desktop computers or car electronics. But today, partners' need for efficient processing have changed dramatically, doubling every couple of years. And accelerating faster now, AI is driving an insatiable demand for compute, demanding specialist processing. Partners building modern SoCs need to configure different specialized processing elements to match their needs. And only Arm is investing to meet partners' needs for a range of processing IP for the lowest cost devices right up to supercomputers. Now today, most machine learning is still performed on Arm CPUs, and we continue to improve their efficiency. But dedicated NPUs are becoming more prevalent because they dramatically improve both performance and efficiency in a world where more and more ML must be run. We're building more flexibility, efficiency, and security into our platforms across all our processors, CPU, GPU, and NPU, to help partners create products for their markets. Massive efficiency improvements mean that we can move applications from supercomputers onto wearables. We are democratizing AI. Where applications require ML for small workloads but maximum flexibility and to be future-proof, we have more CPU extensions. For applications requiring a balance of more performance and good programmability across a wide range of data types, we have GPUs with improved machine learning support. Where workloads demand smaller amounts of ML, we have scalable micro NPUs providing great flexibility, power efficiency, and optimization for the smallest of devices. And of course, we have dedicated NPUs for high demand workloads. Additionally, to protect partners' software investments, we're driving standardization. As our NPU products mature and the ecosystem rallies around a common ARM platform, we're seeing the adoption of our technology grow as our NPUs become a new industry standard. Our NPU products have been designed for scalability and configurability to meet a wide range of performance points, but also for different ML workloads. And as we think about the technologies we bring to the ARM portfolio to support ML in the future, we work closely with the partnership. For example, we work really closely with NXP in defining the original version of the innovative micro NPU Ethos U65, which they just announced will be in their next generation applications processors called Armv9. Future collaboration with NVIDIA, particularly standardization on tools and software, could also increase machine learning choices for the partnership. In the Armv9 decade, partners will create a future enabled by Arm AI with more ML on device. With over 8 billion voice-assisted devices, we need speech recognition on sub-$1 microcontrollers. Processing everything on server just doesn't work, physically or financially. Cloud compute and bandwidth aren't free, and recognition on device is the only way. A voice-activated coffee maker using cloud services used 10 times a day would cost the device maker around $15 per year, per appliance. Computing ML on device also benefits latency, reliability, and crucially, security. AI vision will enable a revolution in agriculture with remote crop monitoring drones, identifying pests and bacteria, and advanced soil analysis devices identifying nutrient deficiencies, helping feed the world. AI, more than any technology, will change healthcare. We enter a decade of transformation with affordable and accurate data-driven sensing devices, delivering vastly improved monitoring and diagnosis. We can easily see AI enabling a 20% or more improvement in healthcare prediction accuracy in the next 5 years. And less publicly visible, but massively important, will be industry. Recent IHS research showed today pumps use 10% of the world's electricity, and 90% of them are inefficient, according to a leading manufacturer. If pumps were a nation, they'd rank third in worldwide electricity consumption. Remote monitoring would require connectivity, but only 1 in 36,000 pumps are currently connected. However, local AI control systems, like the fridge I talked about earlier, can reduce energy by 15 to 20%. Achieving that would represent a global energy saving of 2%. Now, this may not be your robot butler or flying jet car, but that would be seriously cool. Arm is enabling the partners, and together, we're changing the world. Thank you for listening to our vision for AI in the era of Armv9.
Hello, my name is Peter Greenhalgh, and I'm responsible for product technology at Arm. Now, the current tech landscape is evolving at an incredible pace. We see increasingly complex workloads and often heterogeneous workloads in the mobile, auto, and infrastructure markets. While Moore's law is slowing, we're still seeing benefits in power area and frequency as the nodes shrink. However, the nodes are getting more expensive, with a 5nm mask set exceeding $20 million, and it now takes 5 months for a chip to go through the fab. Against this backdrop, there's a requirement that new chips must provide excellent ROI on traditional compute workloads that people care about today, and on the future workloads that people will care about tomorrow. And given the high cost of failure of a tape-out, both in absolute cost terms and also in market window impact, there's also a requirement to be using proven and high-quality IP. So in the decade of V9, we are going to deliver the technology that enables the performance and the quality that the market needs. In recent years, our total compute strategy has worked on improving both traditional and future compute. We achieve this by creating technology that spans the solution of IP we provide, as well as improving the individual IP as well. Like security that is consistent across the CPU and system, and performance optimization across the CPU and GPU to improve gaming. Some of these optimizations can be seen this year with the Cortex-X1 release, and we've got a growing pipeline of technology based on total compute that will deliver into the future. If we take a look at our CPU roadmap over the last 5 to 6 years, we can see an amazing increase in CPU performance that massively outstrips the industry average. In the mobile market, since Cortex-A73 arrived in 2016, there's been a 2.5x increase in delivered performance to the Cortex-X1 devices that are now shipping. The infrastructure market has shown similar gains of over 2.4x increase from 2015's Cortex-A72 to the Neoverse V1 we expect to see in devices later this year. And it's not just about performance either, as the last 5 years of CPU technology have provided improvements in security, efficiency, and scalability. Yet performance remains a key metric, and we're not slowing down as we move to the V9 architecture generation. We expect to deliver more than 30% performance in the next 2 mobile and infrastructure generations on industry standard benchmarks like SpecInt, and with even more performance on the workloads that our mobile and infrastructure partners care about. Yet it's not just about intrinsic CPU performance. Increasingly, we're looking to maximize the performance that the CPU provides through the system design. In fact, we can see more than a generation of CPU performance that can be gained through pushing the path to memory from the CPU. We have developed or are developing a number of technologies that can maximize frequency, bandwidth, cache size, and reduce memory latency to extract the maximum performance of the CPU. Now, what's great about all of this CPU and system performance is that it applies equally to notebook performance as it does to mobile performance. Certainly, notebook performance is a little different from mobile in that it's more thermally permissive, and CPU and GPU performance can be pushed further. Yet, fundamentally, the same principles apply on performance and efficiency. And technologies like Big. LITTLE, which Arm invented, are pretty much an industry standard now and also have a place in the notebook world. In the industry today, there's often a debate about the merits of accelerators to push the performance of compute. Now, there's absolutely a place for compute acceleration, with video processors and the machine learning processors described by Jem earlier being excellent examples of accelerators which are here to stay. Yet looking at the demands of commercial compute workloads, there's a requirement for them to be programmable, which can include everything from libraries and C compilation to virtualization so that they can be easily used in a cloud environment, all the way through to debug and performance analysis. There's also a requirement for them to be protected, and by this I mean secure. Pervasive, so that you can land on many devices, and naturally proven in quality. Now what this means is that by the time you add these features and capabilities to a specialist accelerator that's only applied to a narrow range of workloads, then you're growing its size and becoming very CPU-like. From this perspective, our belief is that we should continue to extend the CPU architecture so that our CPUs can accelerate even more workloads and do so in a way that is programmable, protected, pervasive, and proven. And today, it's impossible to ignore how fragmented some of the AI and DSP workloads are in the mobile market and how they can benefit from being coalesced onto a CPU environment. And this is where we want to push our architecture and compute designs. But it's not just about the CPU. And at Arm, we're very proud of our GPU technology and the part that it plays in total compute. We have new technologies like ray tracing that we will deploy in upcoming GPUs. And of course, for gaming, bandwidth and energy efficiency are super important and will be improved with variable rate shading and new advanced rendering techniques. Going beyond gaming, we're deploying our GPUs into functionally safe automotive environments, and that needs us to provide safety-critical features and also virtualization. Now, bringing this all together, we have huge sustained increases in raw CPU performance across all markets. And we have the technology bandwidth to push GPU performance and architecture higher at the same time. We're not just focusing on the CPU and GPU either, but looking at all of compute, as well as maximizing the performance by deploying new system technologies that provide additional gains. And we are broadening the architecture to execute even more compute, such as DSP and AI on the CPU. So in the decade of V9, we're continuing to deliver large increases in performance and architecture for all workloads, markets, and people. Thank you.